Hello, so here is our video walkthrough for Lab 9B. Now just to note, if you have a version that doesn't say 9B at the front, go ahead and re-download it. I may have rechanged or may have updated the version of the lab. I made the intro example a little bit more applicable to the specific data we have. So here's the difference in our test. We're doing the same thing as Lab 9A, where we tested one proportion, but we're testing two proportions. So it's always a good idea to have previous labs open so you can refer to them. For example, we got our central limit theorem. That's pretty key. We're going to use a variation of that for Lab 9B. Okay, so what are we doing? We got two proportions, just like we did before with Trump and Biden. We had two different rates for them voting, but now we want to see, is there a difference between two proportions? And this test works when we have two different samples. So it's a little different than the previous case where we had the same sample but two different rates that we wanted to compare. Now we have two different groups of people for which we want to compare. Is the difference between the two sample proportions significant? So the conditions for this is we want this value, proportion from sample 1 minus the proportion from sample 2, to be nearly normal. So in order to ensure that, we say we got independence within the groups. We can say that this is randomly selecting people in both groups, and who I select for group 1 doesn't matter for who I select for group 2. And then the sample size needs to be large enough so that we have at least 10 successes in the first group and 10 failures in the first group, and the same for group 2. So that's how we can calculate it. So once we have normality, once we satisfy our assumptions, we can go on to find out something called the pooled standard error. It's a different standard error because we have two different samples we're working with. Think about it this way. We're adding the two different separate variances and then taking the square root of the sum is what that comes from. So here's the example that I've modified for this lab. I think it's more applicable. So we got two different groups of people that we're testing to see whether they voted. So the first group, we got people ages 18 to 24. They voted at a rate of 26% recently. The second group, we have ages 25 to 32. They voted at a rate of 29% recently. So the real question is are these rates significant, or is it no more than you would see from random chance? So to answer that question, let's first check our conditions for nearly normal. So independence, we randomly selected groups. And that says within each group they're random. What about between the groups? Whether or not someone fell into one group or not may not be random because it's the age factor. So to make this a truly random, a truly independent study, we have to pick people first for each group and then make sure we have 100 people that satisfy each condition from each group. So we'll say that's good enough. And then to test the size of successes and failures, let's do it first for group 1. Group 1, that's the 18 to 24. We got P1, although that's P1 hat, but I'm just going to say P1 to be simple. And this is a group of 100 people. So we got P1, 26%, 100 people, and we want to see if N1 times P1, that's the number of successes. I'm going to put a little note here. Successes, people who voted, N1 times 1 minus P1, that's going to give me the number of failures, people who didn't vote. So we can check, did I get at least 10 from each group? Looks like we did. So we can explicitly check that. And then let's do group 2. We can use our work. The only thing that's different is we got 29%. And since we're going to use these variables later on, I'm going to make sure we all say P2 and N2. You'll see why this is. So again, we have at least 10 successes and failures. So based off this, we can proceed with our analysis to find the standard error, which is a different formula. It's square root of n1 times, p1 times 1 minus p1 divided by n1. And then I add the same thing, but for group 2. This is called the pooled standard error. So let's check to see that you get the same thing. Close parentheses for my, oh, I already got one close parentheses. That looks good. There's my standard error. I'll put it on a new line by itself so I can see what it is. Okay, that's a reasonable value. It tells me one standard deviation of my sampling distribution is 0.06. And so now we can find our confidence interval. Confidence interval here, instead of saying p hat, we're going to say p1 minus p2 plus 1.96 times standard error, because this is the parameter we're trying to estimate. What's the difference? So I gave you that formula above, and then we would say minus and plus to find the left and the right intervals. So there's our difference of proportions. So it's interesting. This difference, we test, does it include, talk about a little bit, the null value, which is, we're curious, is there a difference? If that's our question, is there a difference between the two groups? This is kind of specific. Well, there would be a difference if P1 minus P2 is not 0, right? We would say no difference if P1 equals P2, which is the same thing as saying P1 minus P2 equals 0. So if these are equal, the difference will be 0. And since our interval contains 0, boom, ba-doom, 0 is between these two values, we are not sure. Since 0 is in our interval, we are not sure there's a difference. 0 could be a plausible value, so it may be the case that there is no difference between the two. So think about that for a second. But it might help to set up our null hypothesis. Maybe I should have put this problem sooner. So let's look at what the null and alternate hypothesis are. And this is going to be the same for basically any difference of proportion. So the null would say there is no difference between the two groups, right? So that would be saying that P1 equals P2, or that's the same thing as saying P1 minus P2 equals 0. Algebraically, that's the same thing. No difference. The difference is equal to 0. So that 0, that's our null value. That's what we want to test for. So the alternate would say, hey, there is a difference. So P1 is not equal to P2. Or you could say P1 minus P2 is not 0. So that's what our hypotheses are. So you can see, since our null value is contained within our interval, we don't have evidence to reject the null. The null is very plausible. It's plausible that there's a difference, that there is no difference. I'll write that here. That helps. No difference. The null hypothesis is reasonable. Let's see if we can get the same thing using our hypothesis testing with a p-value. This is now where we construct what this distribution looks like and see what's the chance of getting something more extreme than what we observed. What was the difference? Let's just see, what do we observe? We observed a difference of P1 minus P2. We observed a 3% difference, right? So now we're going to say, is this significant? What's the chance of observing this difference given our sample? So to do this analysis, we have to do something a little more complicated. We have to find a pooled proportion. We're going to put these two samples together. We got 100 people from one group, 100 people from another group. We're going to put them together and use that pooled proportion to calculate our standard error. So let's do that. So P pooled, I'm going to call it, would be this formula here. I think I can copy paste this. No, well, no, I can't. I'll just have to say P1 times N1 plus P2 times N2 divided by N. I think it's N plus N1 plus N2. Is that what the formula says? It's kind of a weird one. Yes, that's my formula. That's my pool proportion. So really that's like the average proportion of people voting in general. So it's somewhere between, what was it, 20, 24, and 29. We found 26 and 29. I'm going to keep that information on hand. Okay, so we observe this, a difference of proportions of 3% from the two groups, from which we got our new pool proportion. And now we're going to use that pool proportion to find my SE using another fancy formula. It's the same thing as before, but now we replace both of the standard errors of the pool proportion. So this is how statistics goes. We have to be specific, use these. I'm going to say PP instead of pool. P pool, just because I don't want to write a bunch. We got this very specific formula. Okay. What gives? Well, we don't have to know all the details of the formula. We just have to know how to implement it correctly. So check your work here. Make sure you can find that formula for the pool proportion right here. Using our variables, we have to be careful of what all our variables say and make sure we're putting in the variables that correspond to what we want. And then this tells us something very interesting. Our P1 minus P2, it's distributed normally. This is what our central limit theorem tells us. It's distributed normally as with mean 0. We say there's no difference. The null hypothesis said there was no difference. So we're going to say the mean is 0 and our standard error is this. So now it's time to draw our picture. Here's our picture here. We got our distribution. 0 is the center of it. We got our SE is the standard deviation of our sampling. And we observe something like -3, 0.03. What's the chance of observing this? Or something more extreme? Here we go, let's find that area. So to find that area, try to do it on your own. It's a lower tail, so P norm will be sufficient. We're going to say P1 minus P2, that's the negative 0.03. 0. SE is already saved above. So I guess my p-value, 0.02. Ooh, this test tells us something a little different. The p-value test is a little more powerful. It says, hey, there is a chance, a very low chance, that there's a difference. So p-value 0.02. This says getting so small, evidence to reject the null in favor of the alternate, which states that there is a difference. This means the older group is more likely to vote. We should say older group is statistically I should say older group votes at a statistically significant higher rate. Yeah, we could see just by looking at the data that it's higher, like the older group voted 29%, but it's not until we can do this analysis say that there's a significant difference. Now we know, hey, there's a difference in the two groups. All right, so for the rest of this lab, there's 3 examples, all of which are from the textbook. So you can check your work, but see if you can repeat this process. Now we're just building some like statistical chops for doing these distributions, doing these tests accurately. And so as you're using this, by all means, copy paste the code, but when you copy paste the code, make sure you specify every variable. If you copy paste maybe this line of code here, but you don't go up above and change where I actually defined these things, you're going to get an incorrect answer. So good luck with that. If you have problems or questions, bring those to class next time and we can still look at it. But I'll grade this lab on completion because the answers, as I said, are in the textbook. So it's up to you to go ahead and check them and make sure you're correct. All right. See you later.